Hello class, and welcome to Chapter 2. We'll just go ahead and jump right in. I hope you read the text in advance, at least have an idea of what we'll be talking about. If not, that's fine. I'd rather you review it first, but you don't necessarily have to. So at the top we have literals. We saw what variables were, right? Variables, the value can change, can vary. Literals, the opposite. Kind of the easiest example is a string, at this point anyways, is a string literal. I'll go ahead and put the mumbo jumbo up here. Don't worry about this. It's just tell us which library to use. All right. We saw kind of in our example the cliche hello world. Well, that's a string literal. It's not a variable, right? The value is fixed. It's just a literal. It doesn't have a handle to it. That is a string literal. Verse is a variable, which can then change, right? I put the value of 9 into the memory location pointed by the variable x. Then I put the value 6 into that memory location. So that's kind of the difference. So we saw assignment, right? Go from right to the left. Value 9 goes into the integer type variable x, or the location pointed to by the integer variable x, however you want to think of it. Now another thing, we have an int here, and next is increment decrement. So increment, means to obviously to raise the value by 1, and decrement means to, lower it by 1. So I could say, I could do this, right? And then I could display x, and we get 10. There we go. Oops, I forgot. Let me go ahead and comment that out. There also is a shortcut operator. So now you see where C++ got its name. This shortcut increment operator does not exist in C++. Now, if we display it, oops, sorry, x equal, yeah, there we go, 10. What did I get? Oh, yeah, duh. This is an easier way, actually, to kind of show you. So what I do is I create a new integer y. Y is going to be x plus 1. So here x is 10, and then y will equal 11 because it's going to be 10 plus 1. Oh, darn, sorry. Sorry. There we go. That's an increment. That is what we call a prefix increment. I was doing postfix, and I just wasn't thinking about it. So this is called a prefix increment. If you plus x, what it will do is it will first evaluate the 1 added to x. Then it will push the value in y. However, there's a little nuance. If you do it the other way around, it says int y equals x. Then add 1 to x, but by that time you've already put the value 10 into y. So that's a prefix increment, and this is the postfix increment here. Postfix increment is really useful in loops. Or it's where, many times it's used, where it's very, very useful here. It just basically says, starting at 0, going up to 10, go ahead and add 1 for each loop iteration. So basically this will iterate 10 times. So that's an example of a, prefix and postfix increment operators. Plus plus x or x plus plus. Keep in mind that, when you do plus plus x, then this is evaluated from right hand side first, so you'll have 10. If I do it the other way around, It'll remain the same because it assigned the value x to y and then added 1 to x, which doesn't do anything for me. Yep, there we go. See, it remained 11, 10, 11, 11. Yeah, so when you have variables, I use the x is a pretty good one, so is n, whatever. You want to use descriptive variables, however. Let's say I want to calculate, I don't know, let's say area of a square. And this can work because basically what will happen is the compiler will evaluate the result of side times side, and then concatenate what we call join, concatenate that with the string literal area equals, and push it to the output string. And what did I tell you that? Oh, yeah. So naming convention. Naming is important. So, side, area, these are sensible names. These make sense. If you're going through a program, 36. If you're going through a program as a maintenance engineer, you're going to want to know what things stand for. Trust me, nothing is worse than having obfuscated variable names that mean nothing. Now, there's kind of a you are restricted. They have to start. Sorry. They have to start with something alphabetical or underscore. You can't have 0 to 9 at the beginning. So if I say, I don't know, let's try 0 area. This should not compile. Yeah, that's correct. Yeah, see, unexpected unqualified ID before numeric constant. It says, hey, that's a number, dummy. However, I can do something like this. I can put a number underscore anywhere in that thing, or underscore number, and it compiles everything, works. It can also start with an underscore. Constants generally start and then with underscore. You just can't have a leading number. So you can have A to Z, upper, lower, underscore, and 0 to 9 with, you just obviously can't start with 0 to 9, a variable name. You do have some keywords. Let me see. See, auto is a reserved keyword. The reserved keywords, if you're using an IDE, will generally appear in a particular fashion to you. See this purple here? The fact that it appears purple should have let me know this is a reserved word or a keyword in C++. So the compiler says, hey, what did you want me to do here? Auto what? A list of them, new, auto, whatever the types, data types, etc. Those are all reserved, whereas you can't use those in your variable names. And let's go ahead and talk about further about naming conventions. A couple ways of doing it. If you let's say area, so let's say area of a square, It's kind of sort of all runs together. It's not very readable. But how about this? There we go. How about if we capitalize maybe the first letter of each word? That's called camel case. So that makes it a little bit more readable, right? Area of a square, you can kind of read that, rattle that off without having to look at it first and figure out what it says. Or some people, and I would kind of discourage this, some people like underscores. I don't know. I prefer camel case. It's just more concise. It's kind of less stuff on the screen. But this is certainly legit as well. So it's just a couple things to consider. Don't just kind of jumble all lowercase is basically what I'm telling you. All right, order of ops, kind of order in which these expressions are evaluated. Parentheses first, right? Well, remember, I don't know, if you guys, if you remember from algebra, PEMDAS, please excuse my dear Aunt Sally. So it stands for parentheses, exponents, multiplication, division, addition, and subtraction as far as, evaluation of expressions. And we do have, it's pretty similar in programming languages. Anything within parentheses kind of takes precedence. Here we go. Multiplication is higher than addition. However, parentheses is even higher. Parenthesization, is even higher. So what do you think the result here is going to be? If we apply these, we have parentheses first. Okay, we got parentheses. So everything in parentheses has to be evaluated first. So 6 plus 7 is 13. 5 times 13, therefore, is 65. So I bet this is going to be 65. Actually, we'll just kind of, since we know we can put expressions into the output stream. There you go, 65. Now, how about this? 5 times 6 plus, 56 plus 3, because multiplication is higher than addition. So we do the multiplication first within we look at the parentheses first. Within the parentheses, we do multiplication, which is 56. 6 plus 56 is 62, plus 3 is 65. 5 times 65 is going to be 325, so this should evaluate to 325. Yeah. Now, we can get even more complicated here. So you can kind of challenge yourself with these and do a few of these and see if you can figure out what the result is going to be. So here we have parentheses. I need to evaluate everything inside the parentheses first, but here we have nested parentheses. So I'll start with the nested parentheses. All right, 11, and then I see 6 plus this multiplication expression, since it's higher than addition. 6 plus 7 times 11, which is 6 plus 77, which is what, 83, times 5, which should be what, 415? Let's see. There we go. Yep. All right. Oh, and operators also. If you want to negate something, the unary operator, minus, is going to take precedence. Unary operator takes precedence. Or, well, heck, let's do this. What's an easier way to put this? There we go, 355, because we're looking at 7 times 11, which is 77, minus 6, 71, times 5, 355. But I guess the point, which I didn't make clearly here, is that the unary operator takes precedence. It's the highest precedence. Another unary operator is not. Just keep that in mind. It's a Boolean. It's a Boolean expression. We will kind of discuss that at a later time. Operators PIM order, not a number. Yeah, so division by 0. Yep, and it's not a number. It's a warning. Note it's not an error, so it's still compiled. Oh man, that's a big old error code. So that's just basically saying division by 0. So that's what not a number is, basically, or you could say infinity. Yep. It's That's when you see NaN stands for not a number. If you want to kick, ask Siri what 0 divided by 0 is. You'll like the answer. Data type promotion. So if we have an integer, let's say we have, I don't know, we'll have an int that, I don't know, whatever. We'll give it whatever value. And then we have a double or floating point or whatever. Ooh, how is C++, how's the compiler going to handle this? If I do this, is it going to take the whole thing and display it with the decimals and everything, or is it gonna just truncate, just do the integer part of the multiplication? Well, the answer is that it'll take the more precise type, which in this case is double, and it will do what we call promote the answer to a matching data type. So the answer will be autocast kind of promoted to a double. So 8 times 6.3 is going to be what? 48 plus 2.4 is what? 50.24? Did I do that right? 48, yeah, should be 50.4. There we go. Yep, so the result is kind of cast auto-promoted to a double. So that's an example of data type promotion when they talk about it in the text. And we can display, let's say here, we'll do a whole bunch of decimals. And let's say we only want to display, if we run this, we'll get, see we get a whole bunch of stuff. Let's say I want to only display 2 digits. Well, there's a flag for that. I can put an indicator in the output stream. Let's say I want just 2, hold on. Oh gosh, it's, I think, there we go. There we go. I had to add a new library to it. But, what we can do is we can set the number of, I guess, digits we want to display after, in the mantissa part, after the period, after the decimal with the set precision flag there. We have a fixed flag, and then we specify we want to set the precision, which is after the floating point, to 2, and so that way we round. Excuse me, we truncate rather, I guess, to to 2 digits, to 2 decimals, 2 numbers in the decimal point, in the decimal place here. All right, scientific notation. Aha. So what happens if we have really big numbers? Oh, yeah, that's too big of a number. There we go. There we go. You see our scientific notation there. E plus 0, 1, 2. So what that means is 2. The answer is 2.90874. I'll make sure I have this as a comment so you don't think I'm trying to write code. Times 10 to the 12th. So that's what that means. An easy way to look at this is say, hey, let me take this decimal point and move it over to the right 12 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's my answer. There's my decimal point. That's my answer is, oh God, what is this? 1,000, million, billion. So 2,908,740,000,000. So there's your, there's your explanation for scientific notation. Don't be surprised when you see that. It just means it's a big number. Right, and you can also kind of manually set numbers for scientific notation. I don't know why you do that, but you may have your reasons. Maybe you're a scientist and you want to display it that way. Constant. So a constant is just as the name implies. Going to be, a constant value. It's not going to change. So let's say I want to create a constant. We'll say pi, right? And I don't know. I'm not one of those pocket protector guys that knows all the places of pi, but we'll say 3.1415. That's good enough for me. 3.1452 something 89. The heck if I know. I'm not going to guess. So you see, constants are generally all in uppercase. I like to, kind of starting them with two underscores so that you can see very clearly that it's a constant. Now, well, here, I'll just use it. It is basically, it's the same thing. It's an integer with a fixed, or it's, I didn't, darn. We'll just call it a double. It's a double with a fixed value that cannot be changed. If I try to change it, oops, I should get a compilation error because I declare it to be a constant. Yeah, good. Assignment of read-only variable pi. So here's, kind of an example of using pi. Give me radius, and I'll give you circle area. We can also declare, and we could even assign, if we wanted to. There you go. More than one variable on the same line. And we just, this one, actually, I'm not sure that this will work. We'll try this. We just separate them with a comma. You know what? Yeah, that was a bad move. I didn't think that would work. Okay, fine. So that's actually, all right, here. We'll take the constant out. We'll say, if pi weren't a constant, and if it were the same data type, we could declare them on the same line just like this. And it's not considered stylistically to be bad. What? Yeah, that's right. I didn't. And now it'll compile. It's not considered to be stylistically bad, nor is it a syntax error. So fine. So since this is a constant double, it's actually a different data type, so I'll have to declare it on a different line. So what I want to do, I'll say, hey, I want to put an end line in. Otherwise, remember, my output will kind of be adjacent to the value that I provide as input. So I'll give end line, and then I'll say what, pi r squared. There we go. 10, 3, 4. Yep, that's right, because, r squared is going to be 100 times 3.1415 is 314.15. Now, the good thing about a constant, let's say, and it's not variable, but let's say, interest rate, anything that's that could be used in a whole bunch of places in the program that you may want to change at a later time. So if the value of pi were to change, let's say we kind of came up with, I'll come back to it later. I'll use it in my program for now. It's used in 100 places. I'll get more precision on it. I'll look it up in a textbook. I'll look it up in a math book, and I'll come back with a better definition of pi at a later time. Well, when I come back, I don't want to update 100 different references because I'll miss some. The program will be incorrect then. So if I declare constant and then use the constant everywhere below, what I'll do, I'll just need to say, hey, hey, I found that, I found it in more digits. So now, there we go. We're getting a little bit better. We have a little bit of rounding there. But anyways, you get the point. You can, if you use a constant, it's something that you're using a whole lot in the program. You don't want anybody to change those variables. You only want one unified place here for everything, so that you can change it easily, and it's referenced in the program, and all of the other references follow suit. You can only change it up here. So that's the advantage of a constant. All right, let's see. Library. Hey, this is a library right here. Library is just a collection of functions. The cout, and cin are in the IOStream library. In fact, let me see. There we go. See, cout was not declared in the scope. So they're just pieces of code. So that cout and cin code lies here in the IOStream, what we call the IOStream library. And it's a collection of functions. It's a collection of code that is referenced by the compiler. We don't include all of these because If we did, then the compiled code would be very large because we're including all of our library functions in here. So we only want to include the libraries that we need. IOStream we need for cout and cin. IOmanip I don't need here, but as we saw, if I tried to use some of the IO manipulators, the flags here. There we go. It says, what is set precision? I don't know. Well, I have to import the library. I have to tell it, hey, look in this place, in this particular library. It's what IO manipulation, IO manip, to be able to find the set precision function definition. So that way it looks in IO manip and says, oh yeah, there it is. It kind of links it in, if you will. So that's a couple examples of libraries. We won't be creating our own libraries in this class. It's a little more advanced. Just know that that's what we're doing when we use these include statements. We're telling the compiler, hey, look in these locations in this library for this function. Then you can link it into your program when you're compiling. Okay, math. Yeah. So we got some math functions. Hey, I have one here, pi times radius times radius. Well, what if I wanted to say, give me a number to raise to the nth power? You know what? Here, give me. Aha! I will make it easy. Give me a power to which to raise the number 2. So how would we do that one? Man, we could use a whole bunch of loops and multiply it by itself a zillion times. Well, the easy thing to do in this case would be, since a lot of talented people have already built these libraries for us. Here's a library, math. C language math library. So what I can do, two is what I want to raise to whatever power they give me. So 2, the power function takes 2 arguments. It takes the number to which to raise, and then whatever the power you want to raise it to. In this case, the variable is called power, so we're raising 2 to the power, and the power is going to be variable input from. Oops, you know what? Oh wait. Oh. Here's a quiz for you. Why doesn't cout and cin work? What did I miss? IOStream, right? There we go. And we'll want to, oh, yeah, duh, it's not going to do much good. It's just a statement there. I want to be able to push it to the output stream. Did I do anything wrong? Not syntactically. Let's see. Give me a power to which raise the number 2. We know that 2 to the 10th, as we saw earlier, is 1,024. So let me put in 10, and it gives me, 1,024. So there's the power function. Just know that a function takes input. In this case, takes the number 2, takes a power to which to raise it, and then gives you output, which is this 1,024 in this case. Square root. Give me a number. Give me a number, and I will give you the square root of it. Imagine if we had to calculate the square root by ourselves. That's a good math/programming problem, but we don't have to worry about that. We already have included the C math library, so we'll say cin, let's call this num or something like that. Num, and then we'll cout the square root. That's the name of the function of whatever is given as input. Square root of 9 is 3, right? That's an easy one. So we'll start. There we go. And 4. There we go. 2. Absolute value. And I will give you the absolute value of it. In this case, it's f absolute, floating point. Just a little more useful. Use the f abs instead of the abs, I guess. Negative 9.0, blah, 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 blah. Oh, no. Getting ahead of myself here. What did I say? Negative 9.012 or something like that. There you go. So there's the absolute value of negative 9.012. We know it's 9.012. So these are examples of using libraries. These are library functions. Remember, this is the function name, and then you have your input, your parameters that are passed to it. And it gives you output. Ooh, quadratic formula. Let's make our own. You know what? Let's make our own function. Yeah, so that's a good one. All right. All right, if you know algebra, if you remember, so quadratic formula is negative b plus or minus the root of b squared minus 4ac, all that stuff over 2a. In fact, we'll see it visually just so you your eyes don't glaze over. Come on. Well, here we go. Okay. The roots of the equation, negative b plus or minus a root of b squared minus 4ac all over 2a. So we'll make our own function. So for the quadratic formula, we have variables a, b, and c, right? So what we can do, we want to create our own function. So we have our return type. We want to return a double float because, as we know, we can even have imaginary numbers in there. I'm not going to worry about that right now. But we can create our own function named quad for quadratic formula, and we'll have it accept 3 double arguments, a, b, and c, right? Those are the because you're solving what ax plus b plus c. No, hold on, x squared plus bx plus c. Sorry. So we'll have 3, and I guess it doesn't matter. The math part doesn't matter, but we're accepting 3 coefficients as input: 1 for the quadratic term, 1 for the linear term, and then 1 for the constant term. So basically, as long as we keep this in mind, we're good. So we want to accept 3 values. A, separate the arguments are separated with commas. B, and C. Then we have our braces. We have to have our braces, and in that we have what we call the function body. In the function body is where we do our magic stuff. That's going to be the process part. When we talked about what a program does, it can be the process, it's going to be the code part. It's going to be the algorithm that we use to calculate the return value here. So we know that the roots of our equation are negative b plus or minus a root of b squared minus 4ac all over 2a. Wow. We're just going to return, let's say we'll return the positive root. We'll just make it easy for ourselves. There are a few things to keep in mind. We'll keep it, we'll keep it simple, stupid. So, keeping in mind that we have negative b plus or minus a root of b squared minus 4ac all over 2a. I'm going to start writing this. We'll keep the positive one, right? Negative b plus the root of, what can I do for root? Hey, we have CMath. We have the CMath library that we've imported here. So we could say root b squared, which I could write b times b, or I could say, right, b squared, right? The root of b squared minus 4ac, negative b plus or minus the root of b squared minus 4ac, aha, all over 2a. Why is that a problem right there? Can anybody tell me why this is a problem right here, what I just did? Here we'll have square root of blah, 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 divided, since these are of the same precedence. See, we talked about PEMDAS, and these are about of the same precedence. We will basically calculate square root divided by 2 and then multiply the result times a, and that's not correct. We need to have square root of all this stuff over negative b plus or minus root squared of my b squared minus 4ac all over 2a. Do you see why that's correct? We have to evaluate all of this together divided by all of this together. Or else it will simply go from left to right and say divide all that by 2 and then multiply the result times a. No. We want to divide by 2 times a. So a function has a name, returns a value of a certain type. Here's my return statement. So if we want, we can kind of incorporate this into a whole program. We'll actually call this function. And we could break these up in white space when we input these, by the way, from the front end, as we'll see. As I said, we can put the results of expressions into the output stream. Or here, you know what? So we don't get confused, we'll call these A, B, B, and C, C. And this illustrates an important point that I want to give you. It doesn't matter, it doesn't matter what we call these. These are just variable names here. What it does is it says, hey, I got... What the compiler says is it says, hey, I've got 3 values, 3 double precision values in this order that I'm passing to this function quad. And quad says, okay, I'll take 3 doubles. It renames them here temporarily. So it doesn't matter what you call them, as long as you pass them in the correct order and as long as they're the correct order and type. So let's see if I can come up with, you know what, I didn't comment that out. That's why it's executing, or trying to execute. CC, oh, yeah. Didn't know that those existed. There we go. All right. So let's see, x squared plus bx plus c. I don't know. Oh. Yeah, that's what I was afraid of. We can have... You got to be careful when you choose your values. Well, darn. Negative b plus or minus the root of... Let me make sure the root of b squared minus 4ac all over 2a. Yeah, let's see. What we'll do is let's make sure we got this right. Here we go. Somebody's using an example of 6, negative 17, and 12. Let's try that. Maybe that's a clean one. Yeah, there we go, 1.5. All right. So at least we got the positive root. We didn't get the negative root, but this is an example of a function. Function name, return type, parameters that you input that you have to pass in order and of the correct type, right? Double, double, double. If I were to change these to ints, this would gripe at me. Oh, you know what? No, it doesn't because it's auto promotion. Let's... Yeah, it auto promotes them. Let me see if it complains about loss of... no, it doesn't. Well, that's okay. So you see what happened. It'll take truncation without complaining, and it will it will auto-promote them without complaining here with this compiler. But keep in mind, you make it a warning or worse, with other compilers. They do have to be of compatible types. Here, you know what? Let's do this. I'll just kind of show you with a horrible example. There we go. Now, char can be interpreted as an int, but I still don't think it will like this. It did, actually, yeah, because a character can be interpreted as an int. Here. Aha. Now you're not going to like me. There we go. So it says, hey man, I can't convert a string to a double. I can't cast that up. I can't lose precision. I can't, truncate it. Nothing. So they do have to be of compatible types at the very least. Again, some compilers are more strict about this. Some will probably not even like you trying to, cast or lose precision from double to int, or the other way around. They may complain at you and say, no, I don't want to do this. You have to be more explicit. Function chaining, and we kind of saw this, right? This is an example of kind of chaining functions. You see, I have the square root function, then inside of it, I have another function. So that's sort of function chaining, using functions inside of functions. Perfectly legitimate, because it will execute them, from the inside out. It'll look at the very innermost part here and say, hey, I'm going to raise b to the second power. I'm going to square b and then subtract 4ac from it. Then I'm going to square root this result. Get the square root of this result, subtract b from it, and then I'll divide by, let me see, what's this? 2 times a, okay. And then it'll perform, the division. Right. Integer division, truncation. Yeah. What do you think the result's going to be? Oops, darn. What do you think the result's going to be? I think since you saw truncation, you may have a clue. It's not going to be 4.5. What it does is it truncates, it'll divide, and then truncate the mantissa, kind of everything after the decimal, and so it doesn't round up, right? It doesn't round. I could say 9 divided, let's say 7 divided by 4, which is 1.75. It won't round up to 2. It'll just truncate the rightmost part, so be aware of that. Another interesting operator that we have is the modulo. What modulo division does is it repeatedly divides, it repeatedly subtracts the number on the right-hand side from the number on the left-hand side until it's a number smaller than the number on the right-hand side. The remainder is going to be the modulo remainder. I'll give you an example. 8 modulo 5 is 3. 13 modulo 5 is also 3. Do you see why? We subtract 5 from 13, we get 8. Subtract 5 from that, we get 3. It's more than 5. Or it's less than 5, rather, so there's our answer. It is 3. Where this particularly shines is telling whether numbers even odd. You can get days from this, days of the calendar, days, etc. So here's a good example. And we haven't gone over conditional statements, but don't worry about this. This should make sense to you. Right, so if we subtract 2 from a number repeatedly and we get down to an answer of 1, like for example, 3 minus 2 is 1, 5 minus 2 is 1, 7 minus 2 is 1, then we know it's even. Otherwise, it's odd. 4 minus 2 is 0. 6 minus 2 is 0. So this should work right here. There we go. We could have changed this around. We could say, because this would work, right? 0, otherwise it's 1. Yeah. So that's an example of modular division. You'll see this again. You see this on a test, maybe, hint, hint. All right, division by 0. Yeah, we saw it kind of gives you not a number. It's an infinite number, right? And, a lot of people don't consider division by 0 to be defined. You say, some people, there are a couple of camps, right? One says you can't divide anything by 0. It's 0. There's another camp that says anything divided by 0 is infinity. So it's an undefined operation. That's why you get NaN, not a number. We saw about promotion. You can also explicitly cast a variable to a certain type. There we go. Sorry, I had to pause for a sec. So let's see. Yeah, so we should be able to, let's see, static cast double I. Let's see if this will not complain. Yeah, it doesn't. And so, yeah. This will be more visible if I do this. Oops, darn. Oh, yeah. So here we're going to make it kind of more explicit. There we go. I really should have done this. This will be clearer to you. So what's going on here? I declare double 1.134. I display it. So the first thing it's going to display is 1.134. Then I say, you know what? I want to explicitly cast this, change it to data type integer. And remember, integer does not have a mantissa, so that 134 is dropped off, and you're just left with integer remainder 1. So that's how you cast data types. Oops, sorry. Characters as integers. You saw earlier, remember I sent a character into a function that was a double. What happened was it kind of saw the character as a number. And then it converted that number, that integer, to a double. And that's because, like I said, we have that ASCII table. Where am I? There we go. So we have this ASCII table out there that will give you the number associated with a character. So on the right hand side is a character here. Let's say the capital D is 68. So let's do that. Let's say let's see what happens if we try displaying a character with a value 68. Well, 68 corresponds to that uppercase D. Yep, there it is. Hey, look at that. Now, this can be interesting. Let's see what happens if I do this. Oh, darn. All right. Or Set it cast to an int. Did I not compile? There we go. Static cast, I cast D to an integer, I get 68, or if I cast 68 to a character, I get C. So really a character kind of behind the scenes is an integer value. That's how it's stored in memory anyways. It just knows, the compiler knows, or C++ knows that when it's displaying a character, you don't display the numeric value, you display the corresponding ASCII character. So that's how characters and ints are very related. A character is an int. Outputting, yeah, so if you want to output a quote, quoth the raven, nevermore. That should work, right? Wrong. All right, so what we would need to do is escape these. How do we do that? Remember that escape character? That's it. Now we should see these displayed. There we go. Quote the raven, nevermore. Or if I want to give the raven single quotes, which is incorrect, but whatever. What is? There we go. Oh, and if I want to output a slash, this is a slash, and that's not a guitarist from GNR or anything like that. Guns N' Roses, for those of you that don't know. Uh-oh, doesn't like that, but because it says, hey, you're trying to escape something, dummy, but what are you trying to escape? Well, I'm trying to escape the slash. I want to display the slash. There we go. Backslash, backslash to display a slash, backslash tick to display a tick, backslash or single quote, whatever you want to call it, backslash double quote to display a double quote. String class, I'll kind of hurry along here. I know we're getting along into this video. So the string class requires a new library. It is a whole new thingy, and it is beautiful. Trust me, you don't want to mess around you'll see them. But you don't want to mess around too much with the character, character pointers, with the character arrays, unless you have to. The C strings, the old style C strings. Much safer to use the string class. This way, I can just say, hey, string S equals hello world. C out S. All right, and I can take strings in. I'll just overwrite it because it's a variable, right? And then, all right, hello world. And then it's prompting me for a string. Hi there. There we go. So that's string. Now, string does have a bunch of operations associated with it. These are in the text. I don't believe they're touched on just yet. If you want to read in a string, so check this out. Kind of give some white space there. So check this out. Watch this. Give me a string. Hello world. Uh-oh. Well, all right. It stopped reading the string at the space, at the white space. So how do we overcome that? Get line. So the get line is a function that will read the entire line that you're inputting, including spaces. So I'll take the stream, the line coming from the character input stream, standard input, and read it into variable S. Then I can do whatever I want with S. So getLine is a function that does this. Give me a string. Hello world. Now I hope this works. There we go. Look at that. This is how we get a string with spaces. Instead of just truncating and dropping it at the first space character. So this is much more useful than seeing with the string literal class. This is a fun little experiment here. This will give you the size in bytes of each of these data types. Oh, that's right. Yeah, we'll do this instead. Char. And it's platform dependent, compiler dependent, so we'll see. Your results may not be the same as mine. Okay, so yeah, I really should have here. We'll make this readable, fine. If you have to pause or whatever, I know we've been in this for a while. Keep in mind you can pause me, walk away, continue whenever you want. We've been at this for a while, but that's okay from my end. You do what you need to at your end. Hopefully you're seeing this with fresh eyes or you're still interested. All right, so here we go. From top to bottom, we got character, which we knew was 1 byte. You know, originally I put byte, and then I said, oops, that's not right. Then we have integer, 4 bytes. Now, here's a peculiarity. You'd think that long would actually be a longer value, you know, width-wise, data type width-wise, and being able to store more information than an integer. Well, that's not the case. Long is still 4 bytes of storage. Now, that's the trick. You got to put long in. Then we have 8 bytes of storage, so we can store, you know, up to 64 bits. What's 2 to the 64th? Oh my goodness. And we're not taking into account sign here, but 2 to the 64th. It's quite a number. 1,000 million billion no, 1,000 million billion, trillion, quadrillion, quintillion, 18 sextillion. So if you're taking into account a signed number, 9 sextillion, -9 to +9, give or take. Floating point number is 4 bytes, and double floating precision is 8 bytes on my machine. So that's kind of the data widths here. What was my point? I had up here, oh yeah, integer length versus long length. And so something interesting, you know, you see just this integer that was 4 bytes, 32 bits, right? Here it is. So 2 to the 32nd is 4 million, right? Or 4 billion, right? 4,294,967,296. And really they're signed, so it's actually 2.1 million is going to be the max that we can store in an integer. So watch this. Int I equals, you know what? What did I say? 4,900,000,000. So we'll do something that's definitely too big for an integer to store. See, the compiler warns me. It says, hey, yeah, you're going to overflow, which means that number can't hold all that. Oh man, I got a weird number. Well, yeah, you overflowed. So keep that in mind. If you need to have a corresponding data type, right? If you're going to deal with numbers that you know are less than 2 billion, which I'll explain at a later time. It's not actually 4 billion, but you'll need to, you know, you can use the integer data type. Otherwise, you'll need to use, you know, maybe long. The same with floating and double points. It depends on the size of your numbers, and the limits are actually in the text. You know, in Java, you have max. You can do something like that in Java with a capital I, and it'll give you the max value. In C++, the values are actually contained in one of the libraries, the maximum and minimum values. But yeah, you just keep these in mind. These are the max values. 4.2, well here, 2.1 billion. Same here. 9 sextillion, etc. Float and double are different cases. I think, you know, we have what to the 308 power here. These are monstrous numbers that you're able to store with these two. They are in the text. Unsigned versus signed. Yeah, so unsigned numbers. Like I said, we're not really, you know, if you take 2 to the 32nd, you're at 4.294 million. Well, keep in mind, we have negative numbers that we can use. So we have to basically split this in half and do a lower half and an upper half, because one of the bits corresponds to sign of the number, whether it's negative or positive, and therefore we only have a range of almost 2.15 billion negative up to positive 2.15 billion. Now, if we know we're dealing with positive numbers, you can see the difference. Here we have an unsigned int. Now 4.100000000. So here's 4.1 billion here for int, and then we'll use 4.1 billion positive for an unsigned int. Let's just compile this first and see what this does. There we go. So you see, it did not, for integer, be careful, it did not even warn me here. For integer, did not even warn me. So be careful with the compiler, right? It says, oh, I got a silly value because you overflowed the integer, but the compiler did not warn me because it's only looking for that positive range. However, anything over about 2.1 billion, remember, is going to be out of the signed integer range. However, not unsigned, because remember I said for signed we have to split the value. So we can have negative 2.1 billion to positive 2.1 billion-ish. And then for unsigned, we have 0 up to 4.2 billion-ish, because we're only using the positive values. So here it's 0 to 4.2 billion here. Negative 2.1 billion to positive 2.1 billion, because we kind of split those values since one bit corresponds to sign. So be aware. Random, yeah. So random is in the standard library. It includes a whole host of very useful functions. And I believe we can first use it as is. There you go. So it just gave me a random number 41. Now what happens? Oh, it gives me the same random number each time. Well, it's not. It's a pseudo random number generator. So what I can do is I can seed. Oh, darn. I can seed this with a time value. Oh, yeah, that's right. I need to give it a time. I'll just give it a null. Oh, darn. Yeah, I'll give it a null. There we go. Oh, too many. Oh, because seeded random. So this is going to be the most useful to you as a seeded random. All right, so we saw rand, and it doesn't really produce a truly random number. It'll produce the same one each time. It's a pseudo-random number generator. And we didn't give it a seed value, so it doesn't know really what to look for. It just kind of gives me some random junk. And I can also modulo this, and it'll give me, that means, of course, that it'll, oops, hold on. Give me a number, somewhere from 0 to 4. In this case, 41 modulo 5 is 1, because 41 minus 5 8 times is 1. Now, if we give it a seed of a time value, and this basically means use the current time. Use the current time in milliseconds, or however, whatever, to whatever precision the clock allows. And because that will give you number, that's epoch time here. Yeah, that's epoch time. See how it's giving me progressive numbers? So that these kind of keep incrementing. And so what seeded random does is it says, hey, let me take this time, the number of milliseconds here, or number of seconds rather, and go ahead and run a bunch of calculations on it and make it pseudo-random, chop it up a whole bunch of different ways and kind of, since this number is always changing, it shouldn't give me the same number each time. So now, when I do this with this seeded random number, no match for operator, where am I? No match for operator. Let me make this a little simpler here. I'm missing something. I've been sitting here at the computer a while. Can't really see. Okay, SRAN, and we'll seed it with time with a null. Okay, bear with me here. Sorry, I gotta think about this for a sec. Actually, here, let me try something. Hang on. You know what? I just thought about it. I just have to seed it once. Duh. I believe that to be the case, anyways. And then now that I've seeded it, now let's see what we got. Let me make sure. Sorry, it's been a while. That looks better. If we want a number somewhere between 0 and 55. Then here's how we go about it. All right. There we go. That looks better. Yeah, there we go. All right. Good. So basically, you seed the random, which basically kind of, like I said, chops it up a bunch of different ways and gives it a seed to use for pseudo random generation. Then with each successive call to rand, you should get a pseudo, again, it's not perfect, but pseudo, a somewhat random number. There you go, there's 36. Yeah. Okay. Yeah, in fact, I have it here. I had it here at the next line. Now, there's some mention made in the text of debugging. Oh, by the way, they're incredibly useful for simulations. Do not ever discount this. Don't ever say, what do I want random stuff for? That's crazy. It's so random. But yeah, you will need it for simulations. This is quite useful. Debugging, I love cout statements. If you don't know where stuff went wrong, hey, just litter the thing with cout statements. What you want to do is clean up your code when you're done, right? Do a text search for cout. I love looking at these before or after modification, seeing what values of things are. You can use the debugger. You can use GDB. That's cool. You may want to step through your code. I like cout a whole lot, but debuggers are great as well. You can put, you can kind of pick breakpoints at lines of code and see what values of variables are. We're not going to do that now. That's kind of out of scope here. But you can see a whole lot of stuff that way as well. But I like, for right now, just keep in mind cout, right? You can cout and see what all your variables are and where stuff went wrong. And, you can always comment out code to see, how things change. Maybe you did something wrong somewhere or have some extraneous statements in there. And kind of the last thing they have in there, the auto keyword, I don't like this. C++ is generally speaking a strictly typed language, and that means that we kind of need to, stay within the bounds of the data types that we have. We could do this. You know, here, let's choose a value greater than the value of an int. 8 billion. 6, 7, 8, 9. All right. And so how will we know the data types involved here? An easy way to do, remember I showed you the size of operator? And I'll explain what I'm doing here, the purpose of the above. So the auto operator kind of it defines the type. It sort of figures it out given context. It says, hey, basically says put the value of 6 into the data type of whatever you deem to be appropriate of the variable x. So it says, okay, 6 should probably be an int. Down here it might say, okay, y should probably be a character. And I'll put that in, I'll put that in y. Z should probably be, let's say, a long value since it's greater than the max value of an int. And so we can kind of see, we can prove these and see what size these things are by, we can prove what data type they are, more or less, right, by looking at the size of each of them. There you go. So like I said, 6 is going to be an int. Yeah, an int is 4 bytes as we saw earlier. A char is 1 byte, as we saw earlier, so that's a character. And then Z is a long. Long is 8 in C++. So that's an auto keyword. Don't do this. Don't do this. You want strict typing. This is horrible here. Yeah, there may be some exceptions. I don't know. But you generally don't want to do this. So that's kind of chapter 2. I know it's a lot of stuff. We've been here, oh man, an hour and 11 minutes. So yeah, you're probably sick of me by now. But there's kind of a lot in this chapter. We get more focused and more specific. And they become a little bit more, everything becomes a little bit more cohesive in later chapters because we're getting, kind of more specific, honing in on certain, rather than laying the groundwork, we're starting to hone in on certain aspects of programming and of the language. So I guess with that, I bid you adieu. Let me know if you have any questions, anything at all. Otherwise, yeah, I'll see you in the next lecture. Thanks.